In this video, we'll use the language from the limit definition to discuss when a limit does exist and when a limit does not exist. Let's start by looking at when x is equal to 2. We notice there's an open circle there, so we know that f of x does not exist. But we can look at the outputs for values of x near 2. In fact, we could approximate the height of the hole as accurately as desired by choosing values for x close to 2. The purple dotted lines represent this as accurately as desired bit, and the green dotted lines represent the close enough to 2. In other words, the green dotted lines represent the values for x that guarantee that f of x is within the desired amount of the height of the hole. If the desired accuracy gets smaller, the purple lines will get closer to the hole. If we zoom in a bit, we see that this would mean the green lines would have to get closer to 2. Because we can keep zooming in and repeating this process as much as we want, we can approximate the height of the function as accurately as desired. And we would say that the limit as x approaches 2 of f of x does exist and is equal to some value near 4. Now let's look at what happens when x is close to 7. Can we approximate the height of the function? It looks like we might have two possible candidates for the height. One near y equals 1, and one near y equals negative 0.5. Let's use the definition to help us discuss what's happening here. Let's consider y equals 1 as a possible candidate for the height of the function. If this is a good candidate, we should be able to approximate the height as accurately as desired. Let's pick an accuracy, 0.5. In other words, we want f of x to be within 0.5 of 1. And we want to guarantee this by choosing x close enough to 7. If x is bigger than 7, we seem to be okay. Making x get closer to 7 makes f of x get closer to 1. However, when x is smaller than 7, it doesn't matter how close x is to 7, the f of x values are much farther away from 1 than 0.5. Because we showed that for a desired accuracy, there is no way to guarantee that f of x is accurate enough within 0.5 of 1, we say the limit doesn't exist. There is no way because no matter how close we get x to 7, there are some values where f of x will be too far away. So we say the limit as x approaches 7 of f of x does not exist. And we might use the letters D and E to represent that. You might notice that if x is smaller than approximately 4.5, the function values are close enough again. But think about how we worded the definition. The limit exists if f of x is as close to L as we want whenever x is sufficiently close to C. So we're not going to ignore these values and go for some far away from 7. We want to take all the values between 4 and 7. So if we look at x equals 4.5, yes, f of 4.5 is close enough to 1, but the limit only exists if the function is close enough for all x values between 4.5 and 7. There are other ways to think about limits not existing, but the arguments discussed here have used the definition of limit. When we ask you to use the definition of limit, these are the types of arguments we expect you to make. You should use the phrases as accurately as desired and sufficiently close to C.